And they're off. And we see orange comes out to an early lead, followed closely by purple. Blue and black are trailing. Purple and orange continue in the lead, but here comes blue. Blue's coming up for the pass, makes the pass. Oh man, who's going to take it at the end? What happened there? Looked like black was in trailing the entire time, and did it take it right at the end? Let's zoom in a little bit and find out. Come a little tighter here. Oh man, they're neck and neck. Blue just ahead of orange. Will black take the lead? Let's change our parameters here a little bit. Oh my, right at the end, black sweeps through and takes the finish. So we're going to talk a little bit today about how to create something like this in Desmos. We've been talking about parametric equations. It's actually quite easy to do with parametric equations. We're going to talk a little bit about different growth rates of functions, and we're going to take a look at just how you can make such a tight race like this one. So creating parametric functions in Desmos is pretty easy. What you do is you create a point. So usually a point like if we did, I don't know, like 2, 3. It's going to plot a point like that. But what a parametric equation does is it uses a parameter, which we usually use as t, to be able to graph something like this. So in this case, as t increases, we end up with a line because the x-coordinate will increase at a rate of 2 and the y-coordinate at a rate of 3, which is why it's a steep line. One thing we've been talking about is that you can use cosine and sine to create a circle. So if we use cosine of t and sine of t, you're going to notice that we're only going to get a little bit of the circle because they only have t running from 0 to 1. We want t to run from 0 to 2 pi. That's going to make us an entire circle. So I'm going to, 2 pi is kind of weird to do in Desmos, so 2 pi would be about 6.28. Right there. And then we see we get our full circle. But in my track that you saw, it's not a circle, it's an ellipse. And in order to get that, what we do is instead of just having cosine and sine, you could do like 5 cosine and 5 sine. That would make you a circle that had a radius of 5. But what we're going to do is we're going to make it a little bit wider. So we're going to do 6 cosine and 4 sine. And then we get that nice oval that we had before. Mine was red, but it doesn't really matter what color it is, so we'll just leave it blue. That's fine. So now, what we want to do is figure out how we can get those points to trace around the outside. So the easiest one to do is just to do the exact ellipse as we have it. So I'm going to do 6 cosine, but instead of using t, because it's used to using t for parameters, I'm going to do n. And right away it's going to ask me, do you want to put a slider in for n? Well, thank you, Desmos. Yes, I would. Now what will happen is I can slide that n value, and that will be useful when we're making our point here. So 6 cosine n, and then 4 sine n. And as you see, it puts a point right on there. And right now my n value is 1. If I scroll the n value to different points, it's just going to trace the ellipse, because for any n value, it's going to be on this exact ellipse. It's just going to follow different values, because what this top one is plotting is basically every t value between 0 and 2 pi. And so that gives me the entire ellipse. This guy is saying for a specific value of n, it's going to plot that point, and every single one of those points will be somewhere on the ellipse, so you can see it's going around and around very quickly. So I'm probably going to want to run that also from 0 to 2 pi, so let's do that for now. So about 6.28, and that'll work just fine. So now you see it starts right at the beginning of the race here, and as we increase, it's going to increase and go around at a very steady rate, and then it's going to end up right at the end. So that's not a very exciting one because it just goes at a steady rate. You might say it's kind of linear the way that this goes. As I move n, every time I move it, it's going to move the dot the same distance around. It's not going to speed up or slow down because this n right here is just linear. If I made it 2n and 2n, it's going to move faster because as I increase n, it's going to go around faster, but it's still not going to change speed. So you'll see it's going to go actually around twice now in 2 pi. So you can kind of play with this function on the inside here to see what kind of growth rates you can get, and it's going to just change the speed that the dots go around. And that's really all there is to making this thing. As you can see over here on the left, I have some that are quadratic, I have some that are linear, I have one that's really weird down here. So we're going to kind of see how we come across those. So the first one I'm just going to leave as just 6 cosine n and 4 sine n. So that's just the linear one. It's going to go exactly around once, and that's it. Now I'm going to make one that's going to go just a little bit faster than that. So if I do 6 cosine n and then 4 sine n, so as you saw, if I change it to 2n, that one's going to go a little bit too fast because it's going to go, what did I do? 2n, I need 2n there. So as I go, what's going to happen is the purple one's going to go twice the speed of the green. I don't really want that to happen because it's going to be way out ahead of the green. What I want is just for it to be just a little bit ahead. So instead of being twice as fast, maybe 1.5 times as fast, something like that. So now what's happening is as I increase n, like when n is, I don't know, like 1, the green one is responding to 6 cosine of 1 for sine of 1. The purple is doing 6 cosine of 1.5 for sine of 1.5. So it's already a little bit further along the ellipse. That's the only thing I'm doing. So that's even still a little bit further ahead than I'd like it to be. So what I did in my original example here, you'll see, if I scroll down a little bit, I have a 1.1. So let's do that. So if I do 1.1 and 1.1, that means that the purple is just going to be consistently just a touch ahead of the green. And there you can see I have my purple is just going a smidge faster than the green. So right now, of course, it's going to win, and green will still end right at 2 pi. The purple was a little bit further because 2 pi happened for purple when n was about 5.7, because 1.1 times 5.7 will get you about 2 pi. So now we're getting to the more exciting one. So I was trying to think, as I was making this, what kind of functions grow at different rates? Well, polynomials, if you think about a polynomial, like if you think about a parabola, let's just graph a parabola on here. Why not x squared? So a parabola starts growing pretty slowly, and then it goes faster and faster and faster. I was thinking, hey, that'd be cool. It could be slow initially while the other ones are winning, because if we have a linear, just like 1.1x, so you see initially it's going to be better because it's higher than the black, but eventually the black one's going to pass it. So I kind of use this idea to think, what kind of functions do I have that will initially grow slowly but then grow faster later, because that'll make a more exciting race. So what I'm going to do is, once again, I'm just going to start with I'm going to put this guy up to the top. You can always just drag these to move them if you want to, and then I'll have that as my control all the time. So you can always, if you want to, just start at 6 cosine n, comma 4 sine n. And that gives me, once again, so now I have a blue dot. I might change the color of that. I can go up to the settings here and change this color. Let's make it, I don't know, we don't have a black dot yet. Let's do that. Okay, done. So now, right now, it's just going to be shadowing that blue dot. So the blue and the black, or sorry, green. The green and the black right now are the same thing. So I'm going to mess with this a little bit. Now the problem is if I just make it squared, it's going to go far too fast. So initially it's slow, but it's going to go way, way past them. And that's not very exciting, right? I don't want it to come out and win so quickly. I want it to be very close to them. So what I was thinking about was, how can I make it so that it's a quadratic, but it will still end at exactly 2 pi. It'll still end at exactly 2 pi. So what I need to do to make that happen is I need to somehow make this n squared. When n is 2 pi, I need n squared to also be 2 pi. So if you think about 2 pi being in here squared, what I need to do is get rid of one of those 2 pi's, because I have 2 pi times 2 pi. So what I'm going to do is just divide by 2 pi. And I'll do that over here as well. Now what should happen is it's going to go at a different rate. So I'm going to go all the way back to the beginning. It's going to go at a different rate, so it's going to start slow and get faster, but it should end exactly at the end when I get to 2 pi. So let's see what happens. So the purple and green will start out faster because the linear initially is faster than the quadratic. But what's going to happen is the black's going to speed up as we go, and it's going to end up just catching the green right at the end. Okay? So now what I want is, I don't really want it just to catch the green. I want it to pass the purple right about here. And to do that, you just kind of have to start playing with it. So what I want is, I want this value to be slightly bigger at this moment. To make a fraction bigger, you make the denominator smaller. So let's try subtracting some stuff. Let's try subtracting, I don't know, 1. Right, subtract 1 from both of them. Let's see what happens. So initially, let's see what's going to happen towards the end. So we have the purple and green out front first. The black's chasing it. Now let's see if it's going to pass before the end. So it passes the green, and it doesn't quite pass the purple before the end. So we're going to have to subtract a little bit more. Let's try subtracting 2. A little algebraic trickery here. So here comes the black. It's going to pass the green. Oh, and it passes the purple, but that's a little earlier than I want it. So we need something between 1 and 2. Let's try 1.5. And you can see there's a bit of trial and error here. You can use algebra to figure out when this guy will cross, and then you could figure out the value. But I think it's kind of fun just to kind of mess with it and experiment. That one's pretty close. And I think that might be close enough. But let's make it just a little bit less. Let's do like 1.2. I think that's what I did on my other one. So now, if I do 1.2, what's going to happen is it's going to just pass just before the end of the race, which is kind of more exciting, right? They start at 0. The purple and the green look like they're going to win for sure, and then the black comes because that quadratic will grow faster. Let's see if that's what I did. Yep, looks like I did 1.2. So now, on this guy, the last one, the champion at the very end, so if I change this back to 0 to 2 pi, 6.28, and I run from 0. So the black initially looks like it has no chance. So in this example, the blue is the polynomial one, so it's going to eventually catch up to the green and purple. But the black, look at how slow it's moving. There's like no chance it's going to win. But let's see what happens at the end. The black ends up scooting very, very quickly. The class of functions that does that is exponentials. Exponentials, so if I was to graph just like e to the x on this axis, just e to the x, initially very, very slow, and then it ends up just taking off and growing very quickly. That sounds like exactly what I want. The problem is, well, there's a few problems, but let's start with our classic 6 cosine n, and then 4 sine n, excuse me. And if I change this n instead, so we have an orange dot now, which is perfect because we don't have that yet. So right now that's just shadowing the blue. If I run n, I'm going to move this up so I can kind of work with these together. Oop. The green, excuse me, I keep calling it blue. So if I run n here from 0, the orange and the blue, or green, excuse me, will be right on top of each other. You can't even see the orange because it's hiding underneath the green. So what we're going to do is I'm just going to change this to e to the n and e to the n. Let's see what happens. So you should notice a few things. One is that the orange dot, when n is 0, it's not at 0. We'll talk about that in a second. And also, as I increase, it's just going to go way too fast, right? It's in the lead the entire time. No one ever has a chance. And I want them all to kind of stack up at the end. Look at how many times the orange goes around if I leave it where it is. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9. I can't even count. There's so many. Because by the time that n gets big, e to the like 4th power, that's like 3 to the 4th, that's close to 81. So it's gone around so many times, and there's no way the others are going to catch it. So I want it to be able to kind of be close right at the end there, not having gone around so many times. So the other issue we talked about is that right at 0, e to the 0 is 1. E to the 0 is not 0, so it's not going to start at 0 with everybody else. So to do that, I'll just subtract 1 from both of them. So I have e to the 0 now is 1, minus 1 is 0. So now everybody's starting at the beginning. We still have this issue, though. Right at the beginning, even now, even though it starts slow, the orange is in the lead very quickly. And it's going to stay there. It's not going to come back. So what we need to do is we need to slow this down a little bit. So let's do the same trick that we did with the polynomial. I forgot to close my parentheses there, it looks like. Oh, it did it for me. There we go. So this one, in order to get that 2 pi to cancel, I just thought, how can I make it 2 pi? So this guy is a little bit more tricky. Think about it this way. When n is 2 pi, I want the value of the inside here to be 2 pi. So e to the 2 pi minus 1, what I'm going to do is kind of cheating, but not really. I'm just going to divide it. Oh, if I can get that thing in parentheses. So let's do this. And we're going to divide it by e to the 2 pi. Oh, e to the 2 pi. E to the 2 pi. Oh my goodness. E to the 2 pi minus 1. I'm going to do that on both of them. Divided by e to the 2 pi minus 1. Okay. So what's happening now is by the time n gets to 2 pi, if I actually ran it now, it would be very slow. Notice the orange is hardly moving. And it's going to speed up a little bit at the end, but it still never gets very far. If you remember, that's actually where it used to start, because what's happening is by the time n gets to 2 pi, this cancels out, it's 1. But I don't want it to be 1, I want it to be 2 pi. So how can I make this thing be a 2 pi? I'm just going to throw a 2 pi in front of it. Kind of cheating, but it works out. So what's going to happen now is by the time n is 2 pi, this part will cancel, and I'll just end up with 2 pi. So it should make one complete revolution from 0 to 2 pi. Let's see. So it should catch up very quickly right at the end. Notice it's still hardly even started over here, but in the back stretch here, it's going to go very quickly, and it's going to end up catching up directly to the green. But that's not what I want. I want it to pass. So if you remember, what we did with the polynomial is I just kept subtracting more on the bottom. We're going to do exactly the same here. Instead of subtracting 1, let's subtract 10. Let's see here. Okay, so now if we start, let's see. So the orange is the one we're focused on. And it looks like the black still wins by quite a bit. So the polynomial is still growing fast enough. So what I want is I want that orange to actually pass the black right about there. So I'm just going to kind of keep messing with this. And to do it, I'm going to actually zoom in a little bit. And we're going to try to get that orange further over here. So instead of subtracting 10, let's subtract, I don't know, 20. Okay. Well, let's see here. Well, we're still back here, so that's not going to work. So let's try, I don't know, like 100. It looks like we're going to have to subtract quite a bit here. Okay, so now when n is towards the end, where's our orange? Well, it's getting closer, but we still need it to go move quite a bit. Might have to go to like 200. Okay, well, we're getting closer now. So you see now that we're approaching that value, but I want the orange to be like here right at the end. So let's try like 250. Well, let's try 300 maybe. Actually try this with trial and error, since I actually know the value I want. So if we go to 300, now it looks like we've gone too far. And in order to show it, it's kind of, it's not very smooth right now, is what I want to say. It's kind of broken with where it is. So what I'm going to do is I'm going to change these values to like 5.5 to, let's say, 6. And that'll just be a little bit smoother as I move through there. So at 5.5, you can see it's already passed, which I don't want. I want it to be like in here. So at 300 is too much. So let's try 250. Okay, so now we're down there. Let's see if it passes in time. Oh, the black's going to pass. Let's see if the orange passes. Oh, not quite. So the black is still winning, so we have to subtract just a little more. Let's try 260. You can see lots of trial and error here. Ah, there we go. So let's see here. So let's try the order at the end there. Check this out. So the purple's in the lead, which it's been in the lead the entire time. And then black comes through. That's our polynomial growth. Just passes. And then the orange just passes at the end to win. Kind of cool. So I hope you enjoyed this little screencast about how to use parametrics to make a little track race. If you have any questions, of course, you can always ask me. Hope you guys have a great day and have lots of fun playing with Desmos. Thanks for paying attention.